What if the universe is impossibly older than we thought, and impossibly younger at the same time? For decades, we believed we understood the cosmic timeline. The Big Bang occurred 13.8 billion years ago. The first stars flickered to life hundreds of millions of years later. Galaxies formed slowly, gradually, over billions of years of cosmic evolution. But in July 2022, the James Webb Space Telescope opened its infrared eyes and saw something that should not exist: galaxies. Massive, mature, impossibly organized galaxies, shining from an era when the universe was barely 300 million years old, an era when nothing should have had time to form. The evidence is undeniable, the implications are staggering, and the questions it raises challenge everything we thought we knew about cosmic origins. Today, we journey through evidence that challenges everything. Prepare yourselves. We begin. In December 2021, humanity launched its most ambitious observatory into the void, the James Webb Space Telescope, with a mirror 6.5 meters across, coated in gold to capture the faintest whispers of infrared light from the edge of existence. Its mission: to see the first galaxies, to witness cosmic dawn. But within weeks of releasing its first images, something extraordinary happened. Scientists weren't just seeing distant galaxies, they were seeing the impossible. Dr. Ivo Lab at the Swinburne University of Technology was among the first to notice. Analyzing JWST's deep field observations, his team identified 6 massive galaxy candidates. Their light had traveled for over 13.4 billion years to reach us. This meant they existed when the universe was between 500 and 700 million years old. Young by cosmic standards. But here's the problem. These weren't small, primitive proto-galaxies. They were massive, mature. Some contained as many as 100 billion stars, rivaling the mass of our own Milky Way. According to our cosmological models, this should be impossible. Think of it this way: if the universe's history were compressed into a single year, these galaxies appeared on January 2nd, yet they had the structure and mass of galaxies we'd expect to see in March. The Lambda CDM model, our standard cosmological framework, predicts a slow, hierarchical buildup. Small galaxies form first, then merge over billions of years to create larger ones. Stars ignite gradually, structure emerges slowly from the cosmic web. But JWST found galaxies that appeared to skip this process entirely. Dr. Joel Leja from Penn State University put it simply: these objects are way more massive than anyone expected. We expected to find tiny, young, baby galaxies. Instead, we found galaxies as mature as our own in what was previously thought to be the dawn of the universe. The discovery sent shockwaves through the astronomical community. Some called it the JWST early galaxy crisis. Others wondered if our fundamental understanding of cosmic evolution was wrong. But the evidence forces us to confront an uncomfortable possibility. The universe assembled itself far faster than we ever imagined. Let's examine the evidence piece by piece. Evidence 1: the redshift revelations. JWST measures distance using redshift, the stretching of light as it travels through expanding space. The higher the redshift, the farther back in time we're looking. In February 2023, JADES confirmed 4 galaxies with redshifts above Z equals 10. One galaxy, JADES GS Z13-0, has a redshift of 13.2. This means we're seeing it as it existed just 325 million years after the Big Bang. Light from this galaxy has been traveling toward us for 13.4 billion years. To put this in perspective, if you could travel at the speed of light, it would take you 13.4 billion years to reach where this galaxy was when it emitted the light we're seeing now. Due to cosmic expansion, it's now approximately 33 billion light-years away. Evidence 2: impossible mass accumulation. The galaxy Sears 93316 presents an even stranger puzzle. Spectroscopic analysis suggests it formed when the universe was roughly 250 million years old. Its estimated mass, 100 billion times the mass of our Sun. Consider the timescale. 250 million years sounds like a long time, but in cosmic terms, it's remarkably brief. For comparison, it took Earth's dinosaurs longer to evolve into birds than the entire time available for this galaxy to form. To accumulate 100 billion solar masses in 250 million years, stars would need to form at a rate exceeding anything we observe in the modern universe. The math becomes challenging. Some scientists estimate star formation rates would need to be 10 to 100 times higher than theoretical maximums. Evidence 3. Structural sophistication. But mass isn't the only problem. These galaxies show structure. JWST imaging reveals spiral arms, galactic bars, even signs of multiple stellar populations with different ages. These are features that should take billions of years to develop through gravitational interactions and mergers. Dr. Erica Nelson from the University of Colorado identified galaxies at Z equals 6 to 8 that already possess mature disk structures. These disks show rotational patterns consistent with settled, organized stellar systems, not the chaotic, irregular blobs we'd expect from very young galaxies. Evidence 4. Chemical enrichment. Perhaps most telling is the spectroscopy. JWST's instruments break down galactic light into component wavelengths, revealing chemical composition. Several early galaxies show enrichment in heavy elements, carbon, oxygen, iron. These elements don't exist at the universe's birth. They're forged in the cores of massive stars and scattered through space when those stars explode as supernovae. Finding heavy elements means multiple generations of stars have already lived and died. This requires time. Yet we're seeing this enrichment in galaxies that existed when the universe itself was in its infancy. But this is only one piece of a much larger puzzle. As scientists dug deeper into JWST data, stranger patterns emerged. The density paradox. In October 2023, a team led by Dr. Ivo Labbé published an analysis of 6 galaxy candidates existing between 500 and 700 million years after the Big Bang. Combined, their mass density approached levels that challenged theoretical predictions. According to Lambda CDM, the early universe should have specific mass density limits based on dark matter halos available at that time. These galaxies appear to exceed those limits by factors of 3 to 10. It's like finding a city with skyscrapers before the invention of steel and concrete. The baryon crisis. Here's where it gets truly strange. Baryonic matter, the ordinary matter that makes up stars, planets, and us, comprises only about 5% of the universe. The rest is dark matter and dark energy. But to create the massive galaxies JWST observes, nearly all available baryonic matter in certain regions would need to collapse into stars with unprecedented efficiency. Current models suggest only 10 to 20% of available baryonic matter converts into stars. These early galaxies seem to violate this efficiency limit. Some appear to have converted 50 to 80% of their baryonic matter into stars. We don't have a mechanism to explain this. The quiet quasar mystery. JWST also discovered supermassive black holes in galaxies less than 500 million years old. These black holes contain millions to billions of solar masses. Black holes grow by accreting matter, but there's a limit called the Eddington limit, the maximum rate at which a black hole can consume material based on radiation pressure. Even at this maximum rate, it takes time to grow. Starting from stellar mass black holes, growing to billion solar mass behemoths in under 500 million years requires continuous feeding at or above theoretical limits. It's possible, but only barely and only under perfect conditions. Yet JWST finds these supermassive black holes scattered throughout the early universe, not as rare exceptions, but as apparently common features. The recent confirmation. In September 2024, the JWST Uncover program confirmed these findings aren't flukes. Analyzing gravitational lensing clusters, they identified dozens of galaxies at extreme redshifts, all showing similar properties: high mass, structural maturity, and chemical enrichment. Statistical analysis now suggests these massive early galaxies may be 10 to 100 times more common than previous models predicted. The evidence extends beyond individual anomalies into a systematic pattern. The early universe was not a gradual awakening, it was an explosive burst of structure formation that our theories cannot fully explain. So what does this mean? What theories can accommodate this evidence? The modified cosmology hypothesis. Some physicists propose that our cosmological models need adjustment. Perhaps dark matter behaves differently in the early universe than we assume. Maybe the initial density fluctuations from cosmic inflation were stronger than our models predict, allowing faster structure formation. Dr. Rajendra Gupta from the University of Ottawa suggests modifications to Einstein's equations incorporating tired light concepts combined with evolving physical constants. His model allows for structure formation timescales compatible with JWST observations without abandoning the Big Bang framework entirely. The accelerated star formation theory. Another school of thought focuses on star formation efficiency. Perhaps the early universe had conditions that dramatically accelerated stellar birth. Lower metallicity gas clouds collapse more easily. Denser environments trigger more rapid star formation. Population 3 stars, the universe's first generation, may have been far more massive than modern stars, living fast and dying young, rapidly enriching their surroundings. Computer simulations by teams at the University of California, Santa Cruz show that under specific conditions, star formation rates could temporarily exceed modern rates by factors of 100 or more. But sustaining such rates across hundreds of millions of years stretches credibility. The dark matter variation. Dark matter forms the gravitational scaffolding upon which galaxies build. Standard cold dark matter moves slowly, clumping gradually. But what if early dark matter had different properties? Warm dark matter, self-interacting dark matter, or fuzzy dark matter models all predict different clustering timescales. If dark matter collapsed faster in the early universe, it could create gravitational wells capable of pulling in baryonic matter at accelerated rates, potentially explaining rapid galaxy formation. Institutions like CERN and the Dark Energy Survey are now investigating whether dark matter properties evolve over cosmic time. The controversial alternative. A minority of physicists wonder if the Big Bang timeline itself needs revision. Could the universe be older than 13.8 billion years? Could certain assumptions about cosmic expansion be incorrect? This is controversial. Decades of evidence support our current cosmic timeline, but extraordinary evidence demands we at least consider extraordinary explanations. This forces us to reconsider fundamental assumptions about how the universe transitioned from the cosmic microwave background, a nearly uniform sea of radiation, to the richly structured cosmos we inhabit today. Future implications. The story doesn't end here. JWST continues observing, and new missions are coming. Ongoing research. The JADES program will continue deep field observations through 2025, pushing even farther back in time. Scientists hope to find galaxies at z=15 or higher, potentially witnessing the absolute first generation of stellar systems. The Cosmos Webb survey is mapping larger areas of sky, determining how common these massive early galaxies truly are. Initial results suggest they're not rare outliers, but represent a significant fraction of the early galaxy population. Ground-based observatories like the Extremely Large Telescope, scheduled for first light in 2028, will provide complementary data, measuring precise chemical abundances in stellar populations. Technological breakthroughs, NASA's Nancy Grace Ruhman Space Telescope, launching in 2027, will survey vast swaths of sky with infrared sensitivity. Its wide field of view may discover thousands of early galaxies, providing statistical samples to test competing theories. Meanwhile, the proposed Habitable Worlds Observatory, targeting the 2030s, could potentially image individual stars in some of these distant galaxies, if they're bright enough. What this means for us. Understanding early galaxy formation isn't just academic, it tells us how structure emerges from chaos, how complexity arises from simplicity, how the universe creates environments where chemistry and eventually biology can flourish. If galaxies formed faster than we thought, then the conditions for life may have appeared earlier than we imagined. The first potentially habitable planets could have formed when the universe was less than 1 billion years old. This expands the timeline for cosmic biology. It suggests life may have had more time to emerge, to evolve, to potentially reach across the stars. And it reminds us that the universe is more dynamic, more surprising, more intricate than our equations suggest. But let's venture even deeper. What are the most profound implications of what JWST has revealed? The question of cosmic unity. If massive galaxies formed this quickly everywhere, why does our local universe look so different? The Milky Way took billions of years to reach its current mass. Our galactic neighborhood shows signs of gradual assembly through mergers. Did different regions of the universe evolve at dramatically different rates? Are we living in a cosmic backwater where structure formation was unusually slow? Or are we misinterpreting what we're seeing? Could some of these early galaxies actually be rare, unusual objects that appear more distant than they are due to unusual spectral properties? The anthropic puzzle. The most profound implications emerge when we consider our place in this cosmic story. If galaxies matured this rapidly, then solar systems, planets, and potentially life could have emerged far earlier than previously thought. While Earth formed 4.5 billion years ago, potentially habitable worlds could have existed when the universe was only 1 to 2 billion years old. This means any civilizations arising on those worlds would have had a 10 billion year head start on us. Where are they? The silence of the cosmos becomes even more puzzling when we realize the universe has been potentially habitable much longer than we thought. The simulation question. Some theorists point out that our cosmological models, refined over decades, seemed to work beautifully until we built an instrument powerful enough to actually test them at extreme distances. Could our mathematical models be elaborate approximations that break down at extreme scales and early times? Are we seeing the limits of our equations, the boundaries where human mathematics no longer accurately describes reality? The multiverse connection. String theory and inflationary cosmology predict a vast multiverse, countless bubble universes with varying physical constants and histories. Perhaps the rapid structure formation JWST observes is rare on a multiverse scale. Perhaps we inhabit a universe with unusual properties that accelerated galaxy formation. If so, would this explain why our universe seems fine-tuned for complexity? Would it suggest most universes remain dark and empty while we exist in a statistical outlier? The ultimate unknown. Here's what keeps cosmologists awake at night. We still don't know what 95% of the universe is made of. Dark matter and dark energy remain mysterious. Their properties are inferred from gravitational effects, but their fundamental nature eludes us. If we don't understand 95% of reality, how can we confidently predict how structures formed in the early universe? JWST isn't just revealing distant galaxies, it's revealing the limits of human knowledge. We began by asking, what happens when observation contradicts expectation? The James Webb Space Telescope has shown us a universe that assembled itself faster, more efficiently, and more dramatically than our models predicted. Massive galaxies shining from the cosmic dawn, supermassive black holes appearing impossibly early, structure emerging from uniformity in the cosmic blink of an eye. We know the universe is 13.8 billion years old. We know galaxies exist in the earliest observable epochs. We know our theories must evolve to accommodate this evidence, but we don't know exactly how these galaxies formed so quickly. We don't know if our cosmological framework needs minor adjustments or a major revision. We don't know what this rapid evolution means for the possibility of early life. What we do know is this: the universe is stranger than we imagined. The cosmos revealed by the James Webb Space Telescope is more dynamic, more surprising, more beautifully complex than our predecessors could have dreamed. Every answer births new questions. Every discovery reveals deeper mysteries. The universe is vast. The mysteries are endless. The journey continues.